Hello, my name is Alan Miller, and I will be talking about the radial basis function kernel, or the RBF kernel, today. I will start by briefly refreshing what a support vector machine is and how it works. Then I will introduce the RBF kernel. I will then talk about why we would use the RBF kernel. Next I will cover the RBF kernel, how it works, including the math behind the function. I'll wrap up with talking about an important feature of the RBF kernel, which is the Euclidean distance, and then we'll summarize everything. So what is an SVM or an RBF? To understand the RBF kernel, it's best to make sure to have a basic knowledge of how SVM works. A support vector machine, or SVM, is a supervised learning technique that relies on the use of support vectors to help classify data. Support vectors are the data points closest to the optimal divide of the classes. When trying to find the hyperplane, these data points are given more weight than others. The further away from the class divide a point is, the lower weight it is given in helping to find the optimal hyperplane. One way I like to think of this is using the analogy of war. Our goal would be to separate out the two sides of a battle with a straight line and provide the most distance between the sides as possible. We aren't going to rely on the accounts of the people that are sitting in the back offices to point out and say exactly where the best spot to draw the line would be. We would instead rely on those who were up on the front line and able to see the other side. We would then say that the front line soldiers have the most weight and would be called our support vectors. The ultimate goal of SVM is to find a hyperplane that not only can effectively divide the classes, but also find one that also maximizes the distance between the data in the different classes. That brings us to the RBF kernel. The RBF kernel is the default kernel used by sklearn's SVM classification algorithm. In classification, a kernel is used to transform the data without losing any relationship that may be found in the data to allow for a hyperplane to be fit to separate the different classes. Our hyperplanes exist in the dimension 1 smaller than our data. This means that if we have a two-dimensional data, just x and y coordinates, our hyperplane would exist in one dimension, or as a straight line. Likewise, as shown in this graphic, if we transform our two-dimensional data into three dimensions, x, y, z coordinates, then our hyperplane would also need to transform up one dimension and exist as a 2D plane. This relationship continues through n dimensions, even though our brains really can't comprehend past 3 dimensions. In image A, it would be difficult to draw a hyperplane that could separate the green points from the red points. However, after applying the kernel trick to the data in image B, we see that it not only is easier to draw a hyperplane that separates the data, but we can more easily figure out exactly where the best placement would be to maximize the distance between the two classes. One of the best features of the kernel trick is since we are simply transforming the data into a different dimension, all of the relationships between the points are maintained, and we can simply transform the data back once we are done. You might be wondering why or when we should use the RBF kernel, especially with other kernels available. For datasets that can be easily separated by simple hyperplanes such as straight lines or parabolas, the RBF kernel may not be our first kernel choice. The simpler problems can be more quickly answered by simpler kernels like linear or polynomial. However, even though RBF is not as fast as a linear or polynomial kernels on simple data, it is more robust to complex data. This means that data that can only be separated in n dimensions with complex curves and waves will see a classification improvement when using the RBF kernel. And let's not forget why it's the default kernel used by sklearn. The RBF kernel will still make great classifications on simple datasets. So what exactly is the RBF kernel doing to work so well? It can be explained using the formula mathematical expression E times the Euclidean distance squared divided by 2 times the variance, all of this multiplied by -1. Essentially, each point is being evaluated on how close they are together in distance. The closer the 2 points are, the more similar they tend to be. This is the Euclidean distance represented on a scale of 0 to 1, where 1 means the points are not similar at all, and 0 means the points are the same. The RBF kernel is on the same scale, however it's the inverse. When the RBF is calculated to be 1, the points are the same, and when RBF is calculated to be 0, points are not similar at all. The graphic on the screen shows that as the points in this particular case approach -2, they become more similar. However, as the points begin to pass +2, the similarity gets closer and closer to 0. Points that fall on opposite sides of the hyperplane should have similarity scores at or very near 0. However, points that lie on the same side of the hyperplane should have scores closer to 1. The Euclidean distance is defined as the distance between 2 points. The formula for the Euclidean distance is essentially the Pythagorean theorem. As we previously mentioned, the closer to 0 the Euclidean distance is, the more similar the points are to each other. Unlike the Manhattan distance, the Euclidean distance is not limited to following blocks or grid lines. Euclidean distance is calculated as the crow flies, which is good since the shortest distance between 2 points is a straight line. For each point in the dataset passed to SVM, RBF is calculating this distance relative to all of the other points. In conclusion, we can see that support vector machines are powerful methods that can be used to classify data. Using an SVM kernel trick allows for Hyperplane to have an easier time accurately separating the data points. The RBF kernel is a robust kernel that uses the Euclidean distance to find the similarity of data points. It is more robust to non-simple data than both the linear and polynomial kernels. The Euclidean distance is the distance as a crow flies and can be calculated using the Pythagorean theorem. Thank you.